welcome to what I hope is a short little introduction to network covalent compounds. Call this a level 2 video because it's typically something that's taught at the AP, IB, and freshman chemistry level course. So network covalent bonds are formed by the sharing of electrons between two atoms. So they're covalent in that sharing sense. But they differ from the conventional molecular, what I typically call molecular covalent, by virtue of a long range, very directional network, an ongoing array of covalent bonds arranged in a regular pattern, much like ionics are a regular, predictable array. Okay, so it's on and on and on and on again until you break it. These are not discrete molecules. So for example, your pencil lead is graphite. How long those carbons are going to go on and on and on depends on when you break your pencil. Or if you're in my class, it depends on when I grabbed your pencil and broke it for you, because I break mechanical pencils. So easy. Okay, so substances are like ionic, represented by the smallest whole number ratio, or a formula unit. And the size depends on when this, we'll call it a macromolecule. It's a very, very large molecule, and when that is fractured. Now, band gap theory is an approach to trying to understand network covalent molecules in more detail. If you are in AP or IB chemistry, you don't need to know this, and since that is what I teach, I'm going to be skipping that. You may need to pay really close attention in class or find another video on band gap theory. The table that we're about to see outlines some very common examples, and I think it's in your best interest to memorize a few what I call penultimate examples. A penultimate example to me is one where you already have common knowledge of it. A penultimate example of an ionic compound is table salt. You understand some of the properties of table salt already. And so I think you need to memorize a few of maybe the classic examples. And then the others, we will look at properties that will lead you to an understanding that these are network covalent and not ionic and not metallic, especially with regard to conductivity. They also have a very high melting point, but there's a few exceptions, but most of them do not conduct electricity. To break or to melt, you're actually breaking a covalent bond. And that takes a lot of energy. Unlike molecular covalent, where you're breaking intermolecular forces between neighboring molecules, here we're actually breaking that covalent bond, those shared electrons. It takes a lot of energy to break those. Now for carbon, we have what's called an allotrope. Carbon has many allotropes. One of my favorite is diamond. Allotropes are the same element but different structures and hence different functions. Like an isotope has the same number of protons, different neutrons, and mass numbers. An isomer has the same molecular formula but different structural formulas. So it's that similar concept. So let's take a look at some examples that you really should know. Graphite, diamond, and there's a whole group of compounds called fullerenes. All right, diamond has got an sp3 structure to it. What you can't see in graphite are alternating double bonds, and it has an sp sp2 structure associated with it. And the fullerenes also have an sp2 around the carbons, and this has become nanotubes. It's become a very popular area of research right now to look at fullerenes. It started with Buckminster fullerene, which is, I believe, 60 carbons, and then has moved into nanotubes. Another common one is silicon dioxide. That's sand or glass, and that's an ongoing array of covalent bonds between silicon, oxygen, silicon, oxygen, silicon, oxygen, silicon, oxygen, until you break the glass. Okay, those are the ones you really should know. Silicates have a negatively charged and positive ions in there. So if you can see this one, it's a little small in my video. There's sodium ions in there, and we have negative charges on the silicate instead of silica. We have ions there. And then silicon carbide would be another one. So that gives you some examples of network covalence. And I think they're a fun class of chemicals to study. Thanks for joining me. Good luck with chemistry.